Okay, let me introduce the concept of a twist. If you consider the linear and the angular velocity of a moving frame, at that time the transformation will be a function of time. It means the rotation will be the function of time and the position will be a function of time. In the previous lectures, R dot R inverse is equal to matrix form of the omega s. R inverse R dot is equal to the matrix form of the omega b. This kind of concept will be applied to the transformation matrix. Okay, let's first see what happens when we pre-multiply T dot by the T inverse. Okay, T dot T inverse. In the previous lecture, we have introduced the inverse matrix of the homogeneous transform like this. Then T dot, let's take the T dot. T dot will be the R dot, P dot, and the 3 0 and 0. So 4 0 will appear in the bottom part of T dot. By multiplying both sides, we have the R transpose R dot, R transpose P dot, and the 4 0. R transpose R dot is equal to the matrix form of the omega b in the body frame. R transpose P dot is equal to R inverse P dot. If you apply the subscript of the R matrix and P vector, then we have this one. Inverse is equal to exchange the subscript each other. And then we apply the subscript cancellation rule, then we have the P dot in terms of the B frame. It is equal to VB. So we have this matrix. This matrix has the 16 element because it is composed of 4 by 4 matrix, but independent element will be the 6, 3 omega b and 3 VB. So it can be merged in the single 6-dimensional velocity vector. This vector is called as body twist. By collecting the 6 elements, 3 omega b and 3 VB. So body twist is a single vector belonging to the R6 dimension. T inverse T dot and body twist has some relationship. Both have different dimension, but it has some relationship between both. So actually, if you introduce the matrix form of the body twist, then we will use the T dot, T inverse T dot, okay, using the VB and the omega b. On the other hand, let's evaluate the T dot T inverse. T dot T inverse is equal to like this, using the 2 matrix. By multiplying both sides, we have the 4 element. The bottom part will be the 4 zeros. R dot R transpose equal to the matrix form of the omega s, suggested in the previous lectures. And the P dot minus R dot R transpose P inheres R dot R transpose equal to matrix form of the omega s. Actually, it implies the cross operation between 2 vectors, so it can be written down like this. If you minus sign is inserted to the p, and then we have the minus p. It means minus p cross omega will imply the linear velocity of the fixed frame. So p dot plus omega cross minus p will be equal to the instantaneous velocity of fixed frame. So imagining the body, moving body to be the infinitely large, Vs is the instantaneous velocity of the point on this body at the fixed frame origin, expressed in the fixed frame. Okay, this is the physical meaning of the Vb. By collecting the omega s and the Vs, we can make the six-dimensional spatial twist. Similar to the body twist, the matrix form of the spatial twist is equal to T dot T inverse. It can be obtained 4x4 matrix form of omega s and the Vs. Okay, let's consider the relationship between the Vb and the Vs, body frame and the spatial frame, body twist and the spatial twist. Matrix form of body twist is equal to T inverse T dot. On the other hand, matrix form of the spatial twist is equal to T dot T inverse. Again, here T inverse T dot is obtained like this, and then by applying the subscript cancellation rule, we can get the Vb. Right? On the other hand, we have the similar form of a matrix of a special twist. Okay, this equation will require two matrices multiplication. So it can be changed into just one matrix vector equation. Okay, let's expand this equation. T must be the RP01, and matrix form of the body twist is equal to the like this and the T inverse. As a result, we have this matrix form. In here, this is equal to skew symmetry over R omega B. Actually, this is equal to omega S matrix form. On the other hand, this is the Vs. Okay, from this equation, this matrix form, we can know that omega S is equal to R omega B, and Vs is equal to P matrix form and R omega B plus R Vb. This equation can be collected into the matrix vector form. Then we have this 6x6 matrix like this. Actually, this matrix is called as a joint map. Okay, for given T written by rotation matrix P and P, okay, each adjoint map or adjoint representation denoted by the ADT is defined as a rotation matrix, and the skew symmetry matrix of P times R and R. If we are using the adjoint map, we can change the reference frame from the body frame to the spatial frame. On the other hand, from the spatial twist to the body twist. If you use the adjoint map, just one matrix vector multiplication will bring the exchange or change the frame or change the vector. But if we want to maintain the matrix form, belonging to small SE3, at that time the 2 multiplication still requires. For given 2 homogeneous transformation, at that time the sequential transformation is required. The independent joint map can be multiplied each other, but it can be combined, T1 and T2, and then we take the adjoint map will be the same result. Okay, the inverse of adjoint map can be obtained, T inverse of adjoint map. Okay, maybe we know block diagonal inverse A matrix give here, B matrix and the 0 and the C matrix. At that time the inverse can be obtained, A inverse minus A inverse B C inverse 0 and the C inverse. On the other hand, A 0 matrix, B matrix, C matrix, then inverse can be obtained, A inverse 0 matrix minus C inverse B A inverse and then C inverse. Using this property of a block diagonal inverse, okay, the inverse is obtained, and then this part can be R inverse, R transpose, P and R, and the inverse is required, R inverse. So this is cancelled out. So it can be write down R transpose P. So this is the inverse of this part and the inverse. Like this, we can write down the inverse matrix of an adjoint map easily. Also, if you take the adjoint map of the T and then T inverse adjoint map is applied, then we will get the identity matrix adjoint map. That will be the same. Okay. Okay, let's take the example. Here, R point is given here. This is the rotation axis. Okay, and then the moving car will be rotated with respect to this point. The rotational velocity will be the omega here. Okay, here the RS, the position of R written by the S frame will be the 2 minus 1. So 2 minus 1, 0 is obtained. On the other hand, this point RB can be obtained plus 2 minus 1.4. Okay, the omega S using the S frame, fixed frame, it can be obtained positive direction positive in the G direction, so 0, 0, 2. Okay, the inheres using the right hand rule, this part will be the positive, but the omega is the counterclockwise here, so 0, 0 minus 2 is given. Okay, both data will be given in the problem, and the TSB, okay, let's obtain the TSB from these figures. Okay, the B frame, okay, let's read the XB in terms of the frame S. This part will be the minus X, so minus 1, 0, 0. How about the YB? It's equal to YS, so 0, 1, 0. That will have the opposite sign, so 0, 0, minus 1. And the 4 times per unit x and 0.4 or y direction. So we have this transformation. If you have this transformation, then it's very easy to obtain the body twist from the special twist. On the contrary, we can obtain the special twist from the body twist using the adjoint map. Okay. The special twist can be obtained omega s and vs. In here, the 3 part is the omega s, and the vs is obtained minus rs. Okay, the omega s cross minus rs will be the vs. Okay, this is the vs. On the other hand, the vb is obtained omega b cross minus rb. So this vector is used, minus rb. For given r, we can obtain the minus rb. So vb is easily obtained using the skew symmetric matrix. Then we have this one. So we can get this data. To transform, to exchange the coordinate frame, then adjoint map is required. So adjoint map can be obtained from the R, the 0 matrix, and then P cross R, and then R. So if you know the adjoint map, then the special twist can be obtained from the body twist. The screw interpretation of the twist. Maybe the twist can be described using the 3 parameters. Okay, let's assign the coordinate here. And then this is the screw axis, the direction, movement direction. And the angular velocity is denoted by the theta dot. And let's take the one point. Actually, this point can be chosen anywhere along with this line. Okay, this vector is called denoted by the q. So the omega will be the s direction theta dot. The v will be the s direction theta dot cross minus q plus if you make the screw motion according to the rotation, the screw will go forward. This quantity is called as pitch. Pitch is defined as the ratio of linear velocity over the angular velocity. So the pitch can be obtained along the s direction according to the angular velocity. So these 2 vectors can be collected into the body twist or special twist. So we can write down these 2 equations and we can get it from here. If you decompose the theta dot, we can get this 6-dimensional vector. It is called as screw axis. Okay, but the screw axis requires 3 elements: q, direction of the movement s, and screw pitch h. It is a little bit difficult to describe to define these three elements. So let's define the screw axis as using the normalized version of the twist corresponding to the motion along the screw. If you have the non-zero omega, at that time the twist can be divided by the magnitude of the omega. It means normalized twist in viewpoint of the angular velocity. Okay, if you take this value, it can be used as a screw axis. Unfortunately, you have the pure translational motion. At that time, the omega will be the zero. At the time, we don't have any omega here, so we will choose the magnitude of linear velocity for the normalization. So if you divide this value to the body twist, then we have this equation. Like this, the screw is defined as the unit or normalized screw axis. Okay, like this, this definition will bring the six-dimensional velocity later. Okay, the screw axis is the normalized twist. So let's denote the SA in the plane SA, SB in the plane B. At that time, the other joint map can be used to change the reference frame. Okay, because the screw axis is the normalized version of the twist. I'm sorry, this twist. I'm a little bit confused with this long terminology, I'm sorry.